The morning of January 4th, 1945, broke cold over the airfield at Kobe on the occupied island of Formosa. Lieutenant Tadao Yamamoto, chief engineer of the Imperial Japanese Navy's technical air arsenal, stood beside a peculiar sight. An American F6F Hellcat fighter, tail number 2 to 9, painted in the dark blue of the United States Navy. The aircraft sat remarkably intact on the tarmac, having been recovered from nearby fields after its pilot force-landed the previous morning. Steam rose from Yamamoto's breath as he circled the machine slowly, notebook in hand. For months, Imperial headquarters had been demanding answers. How were American pilots achieving kill ratios that seemed impossible? 19 enemy aircraft destroyed for every Hellcat lost. The numbers arriving from the Philippine Sea, from Leyte Gulf, from every contested sky in the Pacific, told a story that defied Japanese tactical doctrine and challenged everything their fighter pilots had been trained to believe. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. Yamamoto placed his hand on the Hellcat's fuselage, feeling the cold aluminum beneath his palm. This aircraft would be dismantled, measured, tested. Every component would be catalogued. Every system would be understood. Perhaps then they would know why their pilots were falling from the sky in such devastating numbers. But as the engineer opened his toolbox and prepared to begin his examination, he could not have known that what he was about to discover would reveal not a single secret weapon, but an entire philosophy of war that Japan had fundamentally failed to grasp. To understand what the Japanese engineers found inside that Hellcat, one must first understand what they were searching for. By early 1945, the air war over the Pacific had transformed into a systematic slaughter of Japanese aviation. The numbers were staggering, almost incomprehensible. During the Battle of the Philippine Sea in June of 1944, an engagement American pilots would sardonically dub the Great Marianas Turkey Shoot. Nearly 400 Japanese aircraft were destroyed in a single day. The carrier task forces of the Imperial Japanese Navy, once the terror of the Pacific, had been eviscerated. Hellcats alone accounted for nearly 300 kills that day, losses so catastrophic that Japanese naval aviation would never recover. The pattern repeated itself with merciless consistency. At Leyte Gulf in October of 1944, Hellcat pilots again dominated the skies. Commander David McCampbell, flying from the carrier USS Essex, shot down 9 enemy aircraft in a single sortie, his Hellcat absorbing damage that would have destroyed any Japanese fighter while remaining airworthy. By war's end, Hellcats would be credited with shooting down 5,156 enemy aircraft, 75% of all aerial victories claimed by the United States Navy and Marine Corps in the Pacific Theater. The kill ratio itself seemed to defy the mathematics of aerial combat. For every Hellcat lost to enemy fighters, 19 Japanese aircraft fell from the sky. This wasn't the slight edge enjoyed by a marginally superior aircraft. This was dominance so total, so overwhelming, that it suggested something fundamentally different was happening in the skies over the Pacific. Japanese fighter pilots returned from encounters with Hellcats, when they returned at all, with reports that troubled their commanders. The American fighters were fast, but not dramatically faster than upgraded Zeros. They could dive with terrifying speed, but the Zero could still outturn them at low altitudes. Yet, in engagement after engagement, Japanese formations were being torn apart. Veteran pilots who had survived the Solomons campaign, men with dozens of kills to fave their names, were being shot down by Americans who seemed to know exactly where they would be, who coordinated their attacks with uncanny precision, who fought not as individual warriors seeking glory, but as elements of an integrated system. There was something else, too, that troubled Japanese intelligence officers poring over combat reports and interrogations of the few captured American pilots. American formations seemed to avoid their own anti-aircraft fire with remarkable efficiency. They rarely attacked each other by mistake, even in the chaos of massive air battles involving hundreds of aircraft. They appeared on radar screens as distinct, organized groups rather than the confused tangles that characterized Japanese formations. Some intelligence analysts began to suspect that the Americans possessed technological advantages that extended beyond simple airframe performance. The Imperial Japanese Navy had, by 1944, developed a sophisticated understanding of Dallas American aircraft capabilities through the examination of wrecks and a handful of captured examples. They knew about the Hellcats Pratt & Whitney R2800 double Wasp engine, producing 2,000 horsepower. They understood its armor protection, far heavier than anything Japanese fighters carried. They had measured its 6 Browning M2 50 caliber machine guns, each capable of firing 800 rounds per minute. The self-sealing fuel tanks, the bullet-resistant windscreen, the rugged construction that allowed the aircraft to absorb punishment that would disintegrate. A zero, all of these were known quantities. But knowledge of individual components did not explain the systematic nature of American air superiority. Japanese aeronautical engineers were not fools. Many had trained in American and European universities. They understood aircraft design. The Mitsubishi A6M0 itself was a masterpiece of engineering, achieving extraordinary range and maneuverability through brilliant weight reduction. So how were American pilots, flying an aircraft that was heavier, less maneuverable, and frankly less elegant than the Zero, achieving such lopsided victories? This question consumed Japanese military leadership as 1944 turned to 1945. Theories proliferated. Some argued that American pilot training must be vastly superior, though this seemed unlikely given Japan's rigorous pre-war pilot selection and training programs. Others suggested that numerical superiority explained everything. The Americans simply overwhelmed Japanese formations through sheer numbers. While partially true, this didn't account for engagements where American fighters were outnumbered yet still prevailed. A smaller group of intelligence officers suspected something more insidious, that American aircraft possessed electronic equipment that provided advantages invisible to the naked eye. This theory gained credence as the war progressed, and Japan began encountering American radar technology, first captured in the Philippines, later examined in wrecked bombers and reconnaissance aircraft. The realization that Americans had developed miniaturized radar sets, small enough to fit in aircraft, sophisticated enough to detect other planes and direct fighter interceptions, had been profoundly disturbing to Japanese planners who had only belatedly recognized radar's military potential. The captured Hellcat at Kobe represented an opportunity to answer these questions definitively. Lieutenant Charles V. August, the American pilot who had force-landed the aircraft, was now a prisoner of war, on his way to a camp near Tokyo. His Hellcat, miraculously intact after its emergency landing, would tell the story he could not or would not reveal under interrogation. The aircraft had been assigned to Fighting Squadron 44, operating from the light carrier USS Langley. On the morning of January 4th, August had been leading the 2nd Division of Hellcats tasked with strafing Japanese aircraft parked at Kobe Airfield. Over the target, his engine had failed, likely due to anti-aircraft damage, though August himself might not have known the cause in the chaos of combat. He had managed to set the aircraft down in a field near the airfield, relatively intact, before being captured by Japanese soldiers. For the technical air arsenal, this was an extraordinary opportunity. Previous captured American fighters had been either badly damaged or obsolescent models. This was a frontline F6F, the most advanced variant of the Hellcat, equipped with all the systems that made it the scourge of Japanese aviation. More importantly, the pilot had not had time to destroy sensitive equipment before capture, as standing orders required. Whatever electronic systems the Americans were using, they would be intact. Lieutenant Yamamoto's team began their examination methodically, following procedures developed through years of examining captured Allied equipment. First came external documentation, measurements, photographs, analysis of construction techniques and materials. The Hellcat's size impressed them immediately. It was massive compared to the Zero, weighing nearly 12,000 pounds fully loaded versus the Zero's 6,000. This weight came from everywhere: thick aluminum armor behind the pilot's seat, armored glass in the windscreen, self-sealing rubber lining the fuel tanks, heavy engine components, substantial landing gear designed to withstand the brutal forces of carrier landings. They documented the engine carefully, noting how the R2800's 18 cylinders were arranged in 2 rows, how the supercharger forced air into the engine at high altitude, how cooling was managed. They measured the propeller, a massive 13-foot Hamilton Standard unit that translated the engine's raw power into thrust. They examined the landing gear, noting its robust construction and the wide track that made carrier landings more forgiving than the Zero's narrow, hand-cranked gear. The armament received particular attention. 6 Browning 50 caliber machine guns, 3 mounted in each wing, represented firepower that Japanese fighters could not match. Each gun had a rate of fire of 800 rounds per minute. A 2-second burst would send 160 rounds downrange enough to saw through a Zero's unarmored fuselage like paper. The ammunition was also superior. American 50 caliber rounds were loaded with a mix of armor-piercing, incendiary, and tracer ammunition that could penetrate armor plate and set fuel tanks ablaze. But it was when Yamamoto's team began examining the cockpit electronics that they made their most significant discoveries. Behind the instrument panel, mounted in racks that suggested both sophistication and mass production, was an array of electronic equipment, unlike anything in Japanese fighters. There were multiple radio sets where Japanese aircraft typically had one. There was what appeared to be a radar transceiver, compact enough to fit in a fighter yet clearly capable of transmitting and receiving signals. And there, mounted in a shock-resistant housing, was a device that Japanese intelligence had suspected existed but had never examined intact, an IFF transponder. IFF identification, friend or foe, was a system the British had developed in the late 1930s and shared with the Americans. The principle was elegant. A ground-based or ship-based radar would send out an interrogation signal. The IFF transponder in a friendly aircraft would receive this signal and automatically transmit a coded response. On the radar operator's screen, this response would appear as a distinctive mark, identifying the aircraft as friendly. Without the transponder, or with the wrong code, an aircraft would appear as just another radar contact, possibly hostile. The Japanese engineers understood the implications immediately. American pilots operating in formations near their carriers or land bases would be constantly identified as friendly by their own ships and ground stations. Fighter directors aboard carriers could track their own aircraft with confidence, distinguishing them from enemy formations even in the chaos of a major air battle. American anti-aircraft gunners could hold their fire when friendly aircraft approached, confident that the IFF signal meant the contact was genuinely American. But the IFF transponder represented only one piece of a much larger puzzle. As Yamamoto's team continued their examination, they discovered that the Hellcats' electronic systems were deeply integrated, designed to work together as a coordinated whole. The radio equipment wasn't just for pilot-to-pilot communication. It included multiple channels, allowing pilots to monitor both tactical frequencies for their immediate formation and command frequencies, linking them to carrier-based fighter directors. The quality of the radio was also markedly superior to Japanese equivalents: clear, reliable, resistant to interference. Perhaps most revealing was what they found in the Hellcats' onboard documentation and quick reference cards. These materials, which American pilots used for emergency procedures and radio protocols, revealed a level of tactical sophistication that few Japanese pilots enjoyed. There were detailed procedures for forming up after launch, for maintaining formation spacing, for executing coordinated attacks. There were radio callouts for specific tactical situations, pre-planned responses that allowed American pilots to communicate complex information quickly and clearly. The engineers also found evidence of something even more fundamental. American pilots were trained to fight as teams, not as individual warriors. The radio protocols emphasized formation, integrity, mutual support, coordinated maneuvers. The quick reference materials included diagrams of a defensive tactic called the Thach Weave, named after Commander John Thach, who had developed it early in the war. This maneuver, which involved two fighters weaving back and forth to cover each other's tails, had been refined into doctrine. American pilots didn't just know about it, they drilled it constantly until executing it became instinctive. Lieutenant Yamamoto sat in the Hellcat's cockpit as evening fell over Kobe Airfield, trying to absorb what his examination had revealed. The instrument panel before him represented a philosophy of aerial combat fundamentally different from Japanese doctrine. Where Japanese pilots were trained to rely on superior flying skill, individual courage, and the spiritual strength to overcome material disadvantages, American pilots were embedded in a technological and organizational system designed to amplify their effectiveness. The IFF transponder was important, yes. It prevented friendly fire incidents, allowed better coordination between fighters and their carriers, enabled more effective use of radar-directed interception. But it was just one component of an integrated system that included superior radios, better pilot training in formation tactics, more sophisticated command and control from carriers, and an industrial base capable of producing not just aircraft, but the entire electronic ecosystem that made them effective. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. As darkness fell and Lieutenant Yamamoto finally climbed out of the captured Hellcat, he knew that his report to Imperial headquarters would not contain the simple answer they wanted. There was no secret weapon, no single technological breakthrough that explained American air superiority. What explained it was something far more difficult to counter, an entire system of warfare that integrated technology, tactics, training, and industrial capacity into a seamless whole. The IFF transponder was merely a symptom of this deeper reality that America had approached the air war not as a test of individual valor, but as an engineering problem to be solved through systematic application of resources and innovation. The report Lieutenant Yamamoto submitted to the Technical Air Arsenal headquarters in Tokyo arrived 3 weeks after his initial examination. It ran to 47 pages, filled with technical diagrams, photographs, and careful analysis. But the conclusion, buried in the dense technical language that characterized Japanese military documents, was stark. The Hellcat's superiority derived not from revolutionary technology, but from systematic integration of modest advantages across every aspect of air combat. The IFF transponder, which had initially seemed like the key discovery, was indeed significant. The Japanese engineers had carefully dismantled the unit, photographing each component, attempting to understand its operating frequency and coding system. What they found was elegantly simple: a receiver tuned to specific radar frequencies that would detect interrogation pulses from American radars, and a transmitter that would send back a coded response. The codes changed regularly, preventing enemies from spoofing friendly identification. But understanding how the IFF worked was different from understanding why it mattered. Yamamoto's report noted that the transponder operated at approximately 600 MHz, in a frequency range that Japanese radar technology had only recently begun to explore. The Mark 12 IFF system, as the Americans called it, had been in development since 1941 and represented years of Anglo-American cooperation, building on British systems developed during the Battle of Britain. For American pilots, the IFF was simply part of the aircraft, as natural as the throttle or stick. They switched it on during pre-flight checks, verified it was working, and then forgot about it. The system operated automatically, responding to interrogations without pilot input. This seemingly minor convenience had profound implications. American pilots approaching their own task forces never worried about being fired upon by their own ships. Fighter directors aboard carriers could track the location of every friendly aircraft within radar range, vectoring them toward enemy formations or guiding them home when fuel ran low. Japanese pilots enjoyed no such luxury. Without effective IFF systems, they relied on visual identification, radio reports, and timing to distinguish friend from foe. Japanese anti-aircraft gunners, lacking reliable identification systems, often held fire when they should have engaged or fired on their own aircraft in the confusion of battle. During the Philippine Sea engagement, several Japanese aircraft had been shot down by their own fleet's anti-aircraft fire, a bitter irony that IFF technology would have prevented. But Yamamoto's examination revealed something more troubling than the IFF transponder itself: the American approach to electronic systems design. The transponder wasn't an afterthought bolted onto the aircraft. It was integrated into the electrical system from the beginning, with dedicated power supplies, shock mounting to protect it from the violence of carrier landings, and accessibility panels that allowed rapid maintenance. This integration extended to every electronic system in the aircraft. The radio equipment particularly impressed the Japanese engineers. The Hellcat carried multiple radios, a VHF command set for communication with carriers and ground stations, a UHF set for inter-aircraft communication, and guard receivers that monitored emergency frequencies. Each radio had backup crystals for different frequencies, allowing rapid channel changes. The quality of transmission was exceptional. Pilots could communicate clearly even at long ranges or in the electronic interference of combat. Japanese aircraft, by contrast, typically carried a single radio of indifferent quality. Many pilots simply turned them off, finding them unreliable or the transmission quality too poor to be useful. The cultural implications of this difference were profound. American pilots who couldn't communicate effectively with their wingmen or controllers were at a severe disadvantage. Japanese pilots often viewed radio communication as secondary to visual signals and formation flying, a traditional approach that had worked well in the early war, but proved increasingly inadequate as the scale and complexity of air battles increased. The examination of the Hellcat's cockpit layout revealed another dimension of American thinking. The instrument panel was logically organized, with critical flight instruments directly in front of the pilot and secondary systems arranged by function. Circuit breakers were clearly labeled. Emergency procedures were printed on placards throughout the cockpit. The design assumed that pilots might be stressed, disoriented, or injured, and needed clear, immediate access to information and controls. Japanese cockpits, while functional, reflected different priorities. They assumed highly trained pilots who had memorized procedures and could operate by feel and instinct. This worked brilliantly when Japan had a surplus of expert aviators. But by 1945, as pilot quality declined under the pressure of mounting losses, the lack of user-friendly design became a significant liability. Lieutenant Yamamoto's team also discovered evidence of American quality control and standardization that bordered on the obsessive. Every component in the Hellcat bore identification numbers, manufacturing dates, and inspection stamps. Parts were interchangeable between aircraft. Maintenance manuals were detailed and comprehensive. This standardization meant that American aircraft could be maintained by relatively inexperienced ground crews with high reliability. It also meant that damaged aircraft could be repaired quickly using parts from other aircraft. Japanese manufacturing, struggling under resource constraints and bombing campaigns, could not match this level of standardization. Parts often required hand-fitting. Maintenance documentation was less comprehensive. As the war progressed and Japan's industrial capacity declined, this gap widened. American pilots could trust that their aircraft had been maintained to exacting standards. Japanese pilots increasingly flew aircraft that were patched together, underpowered due to poor quality fuel, and maintained by ground crews working with inadequate tools and parts. But perhaps the most significant discoveries came not from what was in the Hellcat, but from what Yamamoto's team learned by studying American tactical doctrine through the documents and materials found in the aircraft. The quick reference cards, the radio protocol sheets, the formation diagrams, these revealed an approach to fighter combat that was fundamentally different from Japanese doctrine. American fighter tactics, as the documents showed, emphasized mutual support above individual heroics. The basic fighting unit was not the individual pilot but the Section 2 aircraft working in coordinated pairs. These sections were combined into divisions of 4 aircraft, and these divisions operated within larger formations, all linked by radio and coordinated by fighter directors who had the big picture from radar. The thatch weave, documented in the Hellcats materials, exemplified this philosophy. When attacked, 2 American fighters would turn toward each other, weaving back and forth. Any enemy aircraft that pursued one fighter would find itself flying into the guns of the other. The maneuver sacrificed offensive potential for defensive effectiveness, trading the chance for individual glory for collective survival. It worked because American pilots trusted their wingmen implicitly and trained the maneuver until it became instinctive. Japanese fighter tactics, evolved through campaigns in China and refined in the early Pacific War, emphasized individual skill and offensive aggression. Pilots were trained to exploit the Zero's superior maneuverability in one-on-one combat. The basic tactical unit was 3 aircraft, with less emphasis on mutual support and more on giving expert pilots the freedom to engage as they saw fit. This approach had been devastatingly effective when Japanese pilots were better trained than their opponents and flew superior aircraft. But by 1944, neither condition obtained. American pilots, while perhaps not as individually skilled as Japan's pre-war elite, were adequately trained and flew aircraft that negated the Zero's advantages. More importantly, they fought as teams, using tactics specifically designed to counter the Zero's strengths. An American pilot in a Hellcat didn't try to outturn a Zero. Instead, he used his aircraft's superior speed and dive performance to engage on his terms, attacking from altitude, making a single devastating pass, and then climbing away before the Zero could respond. If a Zero got on his tail, his wingman would be there, weaving to cover him. The mathematics of this tactical difference were brutal. A Japanese pilot, no matter how skilled, could only engage 1 or at most 2 opponents at a time. American pilots fighting as integrated pairs could engage multiple opponents simultaneously, covering each other, setting up crossing shots, denying the Japanese the turning fight they needed to win. And when American divisions of 4 aircraft engaged Japanese formations, the difference was overwhelming. Lieutenant Yamamoto's report included an analysis that must have been particularly bitter for Imperial headquarters to read. He noted that the captured Hellcat carried sufficient fuel for approximately 6 hours of flight, with provisions for external and drop tanks that could extend this further. The aircraft's combat radius exceeded 400 miles. This meant that American carriers could remain far from enemy airfields, outside the range of Japanese land-based bombers, while their fighters ranged freely over vast areas. Japanese fighters, optimized for range at the expense of armor and firepower, could theoretically fly even farther. But theory diverged from practice. Japanese pilots increasingly flew in poorly maintained aircraft, burning poor quality fuel, with inadequate navigation equipment and radios. American pilots flew aircraft that were mechanically reliable, properly maintained, and equipped with radios that allowed them to call for help if they became lost or damaged. The result was that American effective combat radius far exceeded Japanese capabilities, despite seemingly inferior range on paper. The examination also revealed the Hellcat's provision for offensive weapons beyond its machine guns. Hardpoints under the wings and fuselage allowed the aircraft to carry rockets or bombs, transforming it from a pure fighter into a multi-role strike aircraft. This flexibility meant that the same aircraft could conduct fighter sweeps, escort bombers, or attack ground targets as the tactical situation demanded. Japanese fighters, increasingly limited to pure air defense roles as fuel and resources dwindled, lacked this flexibility. As spring 1945 arrived and Yamamoto's team completed their examination, they made one final, crucial observation. They test flew the Hellcat carefully, from a Japanese airfield, with full knowledge that American fighters might intercept them at any moment. The test pilot, a veteran of carrier operations in the Solomons campaign, reported that the aircraft handled beautifully. It was stable, predictable, and forgiving of pilot error. The controls were well harmonized. The view from the cockpit was excellent. Most importantly, the aircraft was not difficult to fly. This simplicity of operation was itself a form of superiority. American training could take relatively inexperienced pilots and make them effective in the Hellcat. The aircraft's stability and forgiveness meant that pilots under stress could still fly it well. Its ruggedness meant that pilots made mistakes and survived, learning from their errors rather than dying from them. Japanese fighters, by contrast, rewarded skill but punished mistakes harshly. The Zero was unforgiving of errors. Its lack of armor meant that pilots hit by enemy fire often died. Its tendency to catch fire when hit discouraged the aggressive tactics that might have countered American advantages. As Japan lost experienced pilots and replaced them with hastily trained recruits, this difference became catastrophic. The young pilots arriving at frontline units in 1944 and 45 had received perhaps 60 hours of flight training compared to the 300 or more hours that pre-war pilots had received. These novice aviators were expected to fly complex aircraft in combat against battle-hardened American pilots, flying, forgiving, well-designed fighters backed by superior technology and tactics. The result was predictable. They died in staggering numbers, often on their first or second mission. American pilot training, by contrast, had been massively expanded and systematized. The United States had established a pipeline that transformed civilian volunteers into competent fighter pilots in approximately 1 year. More importantly, experienced pilots were rotated back from the front lines to serve as instructors, transferring hard-won tactical knowledge to new generations of aviators. This meant that American pilots arriving in the Pacific in 1944 already knew about the Zero's strengths and weaknesses, already knew the thach weave and boom and zoom tactics, already understood how to exploit their aircraft's advantages. Lieutenant Yamamoto's final report, completed in April 1945, ran to nearly 200 pages when all technical appendices were included. It represented thousands of hours of work by dozens of engineers and technicians. The conclusions were methodical, carefully documented, and devastating. The F6F Hellcat, Yamamoto wrote, was not a revolutionary aircraft. Its engine, while powerful, was not dramatically more advanced than Japanese equivalents. Its airframe, while rugged, employed conventional construction techniques. Its armament, while formidable, was not beyond Japanese manufacturing capability. Even the IFF transponder, while sophisticated, was conceptually simple and within Japanese technological reach. What made the Hellcat devastating was that it represented the integration of all these elements into a coherent system, supported by superior industrial capacity, better training infrastructure, more sophisticated tactics, and a philosophical approach to warfare that emphasized systematic optimization over individual heroism. The 19-to-1 kill ratio did not reflect a 19-to-1 advantage in any single area. It reflected cumulative advantages in dozens of areas, each modest individually but overwhelming in combination. The report noted that Japan could not simply copy American approaches. The industrial capacity required to produce aircraft with the Hellcat's quality and in its numbers did not exist and could not be created under current circumstances. The training infrastructure to produce American-quality pilots would take years to establish. The The cultural shift required to emphasize teamwork over individual skill would require rewriting fundamental assumptions about aerial combat. The electronic technology necessary for IFF systems and sophisticated radios required expertise and resources Japan did not possess. In effect, Yamamoto's report documented not just the Hellcats' technical characteristics, but the reasons Japan was losing the air war. The captured aircraft was a symptom, not a cause. It revealed that American air superiority rested on foundations that Japan could observe but not replicate: industrial might, technological sophistication, systematic training, and tactical innovation, all working in concert. Continuation, Part 3. The report reached Imperial headquarters in Tokyo in late April 1945, where it was read with grim resignation by officers who already knew Japan was losing the war. By this point, American B-29 Superfortress bombers were burning Japanese cities with impunity. The Imperial Navy's carrier force had been reduced to floating targets, lacking aircraft, pilots, and fuel. The Hellcat report confirmed what everyone suspected but few wanted to acknowledge: that Japan's qualitative edge in the early war had been systematically erased by an opponent with superior resources and a more sophisticated approach to modern warfare. Several officers in the technical air arsenal proposed immediate research programs to develop Japanese equivalents to the systems found in the Hellcat. They argued for crash programs to develop improved radios, Japanese IFF systems, better pilot training protocols. These proposals were quietly shelved. Japan in spring 1945 lacked the industrial capacity, the time, and increasingly the will to implement such programs. The war had moved beyond the point where incremental improvements could matter. Lieutenant Charles August, the Hellcat pilot who had force-landed at Kobe, survived his captivity and returned home after the war. He would later learn that his aircraft had been extensively studied by Japanese engineers, though he never knew the details of what they had discovered. August went on to a career in civilian aviation, eventually working as an air traffic controller. The irony that his captured Hellcat had revealed to the Japanese the very systems like IFF that made civilian air traffic control possible was likely not lost on him. The captured Hellcat itself had an interesting fate. After the examination was complete, it was painted with Japanese markings and flown several more times by test pilots evaluating its capabilities. In August 1945, after Japan's surrender, American occupation forces discovered the aircraft at Yokosuka Air Base, still bearing its incongruous combination of Japanese and American markings. It was photographed extensively, then scrapped along with thousands of other aircraft, as the former enemies began the process of reconstruction. But the knowledge the Hellcat represented did not die with the aircraft. In the years following the war, as aviation technology advanced and the Cold War began, the lessons learned from examining captured equipment became part of the institutional knowledge of air forces worldwide. The integration of electronics into fighter aircraft, pioneered by the Americans during World War II, became standard. IFF systems evolved into more sophisticated forms, eventually becoming the transponder systems that regulate civil aviation to this day. The emphasis on pilot training, standardized tactics, and team-based combat became universal. The 19-to-1 kill ratio achieved by the Hellcat remains one of the most lopsided statistics in the history of air combat. To understand its significance, one must understand what it represented beyond the simple mathematics of kills versus losses. It represented the outcome of a systematic approach to warfare that integrated technology, training, tactics, and industrial capacity into a coherent whole. It represented the triumph of methodical preparation over improvisation, of team-based tactics over individual heroism, of industrial might over spiritual determination. For Japan, the lessons were bitter but eventually transformative. The post-war Japanese approach to manufacturing, with its emphasis on quality control, standardization, and continuous improvement, drew consciously on observations of American industrial methods that had produced aircraft like the Hellcat in staggering quantities without sacrificing quality. The Japanese electronics industry, that would eventually dominate world markets in the late 20th century, had its roots partly in the recognition, forced upon engineers like Yamamoto, that Japan had fallen behind in this critical technology. For the United States, the Hellcat's success validated an approach to warfare that would characterize American military doctrine for the remainder of the 20th century. The integration of superior technology, thorough training, and systematic tactics to achieve decisive advantages. The 15 Eagle, F-16 Fighting Falcon, and F-18 Hornet fighters that dominated late Cold War and post-Cold War aerial combat were direct descendants of the Hellcat, not just in form, but in philosophy, rugged, reliable, technologically sophisticated aircraft designed to be flown by well-trained pilots fighting as integrated teams. The specific discovery of the IFF transponder in the captured Hellcat became part of the legend surrounding Japanese technical intelligence efforts. In reality, Japanese engineers had suspected that American aircraft carried such devices and had captured partial examples before. What made the Kobe Hellcat significant was not the discovery itself, but the context it provided. The realization that IFF was just one component of an integrated system that included radios, radar, fighter direction, and tactical doctrine all working together. This integration was perhaps the most important lesson of all. Modern warfare, as the Hellcat demonstrated, was no longer about individual weapons systems, but about systems of systems. The fighter aircraft was not an independent platform, but a node in a larger network that included carriers, radar pickets, command posts, maintenance facilities, training schools, and industrial bases. Victory went not to whoever built the most elegant individual weapon, but to whoever could most effectively integrate all the components of military power. The Japanese engineers who examined the Hellcat understood this, even if their superiors were not always ready to accept the implications. Lieutenant Yamamoto's report made clear that matching American air power would require not just building better aircraft, but transforming Japan's entire approach to military aviation. It would require massive investment in electronics research, complete reorganization of pilot training, cultural changes in how fighter tactics were conceived and executed, and industrial reforms to improve quality control and standardization. In April 1945, with American forces preparing to invade the home islands, such transformations were impossible. But the captured Hellcat's greatest significance may be what it revealed about the nature of technological advantage in modern warfare. The aircraft contained no secret weapons, no revolutionary innovations that Japanese engineers could not understand. Every system in the Hellcat had been examined, measured, and comprehended. Yet understanding the technology was not the same as being able to replicate its effectiveness. The Hellcat's dominance rested not on mysteries but on the systematic application of known principles, backed by resources and organization that Japan could not match. This lesson would resonate throughout the remainder of the 20th century. During the Cold War, the Soviet Union would obtain American technology through espionage and defection, examining it in exquisite detail. Yet simply possessing the technology did not grant equivalent capability. The difference lay in the systems surrounding the technology: training, maintenance, tactics, doctrine, and the industrial base to sustain it all. The Hellcat had revealed this truth in 1945, though it would take decades for its full implications to be understood. For the fighter, pilots on both sides, the statistics and analysis mattered less than survival. American pilots flying Hellcats knew they had a significant advantage, and this knowledge translated into confidence. Japanese pilots facing Hellcats knew they were outmatched, and this knowledge bred desperation. By 1945, many Japanese fighter pilots were flying kamikaze missions, having concluded that suicidal attacks offered better odds of inflicting damage than conventional combat. This grim calculation reflected not defeatism, but mathematical reality in air-to-air combat against Hellcats and Corsairs. Japanese fighters were being destroyed at unsustainable rates. The 307 Hellcat pilots who achieved ace status 5 or more aerial victories represented not just individual skill, but the effectiveness of a system designed to produce skilled pilots consistently. Commander David McCampbell, the U.S. Navy's leading ace with 34 victories, flew the Hellcat almost exclusively. His success was not anomalous, but exemplary. The aircraft was designed to allow good pilots to become excellent, to allow average pilots to survive and improve, and to maximize the effectiveness of well-executed tactics. Japanese aces, by contrast, became increasingly rare as the war progressed. The handful of surviving elite pilots from the early war period were unable to train sufficient replacements before being killed themselves. The systematic approach to pilot training that the Americans had implemented, rotating experienced pilots home to train new ones, standardizing tactics, emphasizing teamwork, did not align with Japanese cultural assumptions about how warriors should be developed and employed. Japan kept its best pilots at the front until they died, wasting their knowledge and experience even as American pilot quality steadily improved through knowledge transfer. The industrial dimension of the Hellcat's success cannot be overstated. Grumman produced 12,275 Hellcats during the war, at a peak rate of more than 1 aircraft per hour. This production was achieved while maintaining consistent quality, with standardized components and rigorous inspection protocols. Japanese aircraft production, by contrast, declined throughout the war as bombing disrupted factories and resources became scarce. More critically, quality became inconsistent as skilled workers were drafted and materials shortages forced compromises. American pilots could trust their aircraft. Japanese pilots increasingly could not. This disparity in production meant that American losses could be easily replaced, while Japanese losses were irreplaceable. When a Hellcat was shot down, another was available. When a carrier air group was depleted, it was quickly rebuilt with fresh pilots and new aircraft. Japanese losses, particularly of trained pilots, could not be made good. By 1945, Japanese fighters were being flown by pilots with minimal training, facing American pilots with hundreds of hours of flight time in aircraft that were technically superior and numerically overwhelming. The examination of the captured Hellcat thus revealed not a secret weapon, but a systematic approach to warfare that Japan, despite understanding it, could not counter. The IFF transponder was symbolic of this approach, a modest technology, elegantly implemented, integrated into a larger system, produced in quantity, and employed effectively through superior training and tactics. It represented the American way of war, pragmatic, industrial, systematic, and devastatingly effective. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.